Welcome to EPG Pachala. I am Dr. Venusatini from the Department of Philosophy, University of Hyderabad. This is Logic 1. I'll be talking on the module Natural Deduction Presentation of Standard Truth Functional Sentential Logic, and the module is written by Professor Ranjan Mukhopadhyay. In the modules that we have seen earlier, we have constructed a formal language, artificial language for sentential logic. Along with that, we also have introduced a set of rules for checking the validity of arguments in that system. And we have two kinds of rule actually. One is rule of inference, the other is rules of replacement. Together we have 19 rules of replacement. Now in that system we were asking the meaning of validity. How do we understand this meaning of validity? And in connection to that, we try to respond by saying that by the employment of those rules of replacements and rules of inference, to say that an argument is valid. The natural question is, how do we understand these rules? For this, we go back to truth table. We have seen that by constructing a truth table, we can define the meaning of those truth functional connectives. Now, this meaning is being supplied from outside the language that we have constructed. In other words, semantic is an extra logical factor. So this is one approach that we have seen before. In this module, we are going to take another approach, the alternative approach, where we don't want to deal with meanings or semantics. Rather, we want to understand the functions of those truth connectives just by looking at the inferential moves that we can make using those sentences involving connectives. The former method, which I have said before, which is to do with truth tables and validity and things like that, this is called semantical approach. The approach that we are going to explore here is called syntactic approach. That is purely trying to understand the meaning of expression within the language system itself. Now, in the syntactic approach, which is also called proof theoretic approach, there are two ways in which we can understand the function of the truth functional connectives involved in a sentence. One way is we can infer a sentence using a connective from other sentences without those connective. The other is to infer a sentences from a connective, a sentence involving connective, and then inferring a sentence without using connective. In the former case, we are trying to introduce a new connective. In the latter case, that is, we are inferring a sentence without a connective. So we are trying to eliminate a connective. Accordingly, in the first case, where connective is being introduced, it is called introduction rule. In the latter case, where we infer a sentence without involving connective, it is called elimination rule. Introduction rules can be said to be manifesting the ground upon which a sentence involving connective is inferred. And the elimination rule can be shown to be manifesting the consequences of a sentence involving a connective. With the help of some examples, now we will try to explain what these rules of introductions and eliminations are about. With the help of a conjunction, we will try to explain this rule. You look at the PowerPoint. The introduction rules for conjunction. A, if we have a sentence A and then another sentence B, and these are shown to be true. In other words, these are proved to be true. Then from there we can infer the conjunction of A and B, or given the sentence A and another sentence B which are both shown to be true, or for which we have given a proof already, then we can infer the conjunction of B and A. With the same example of conjunction, now let me explain the rule of elimination. Suppose we have a conjunctive sentence A conjunct B, and this sentence is shown to be valid or true. We can infer the conjunct A, which is one of the conjuncts of the conjunctive sentence. Also, we can infer the other conjunct B given A and B. Now, this is just an example. From here, we go on to show that all the truth connectives used in the sentential logic can be explained in terms of either elimination or conjunction. We have done for conjunction, and we are going to do for the rest of the truth functional connectives. Now let us look at those truth functional connectives. I'm going to introduce negation introduction. Given, suppose we have a sentence A and then it results in some kind of absurd statement, then we can infer the falsity of that sentence A. In this, what we are doing is actually we are introducing negation as a truth functional connective. How do we eliminate negation? There are two ways. One, if we have a sentence A and then also another sentence negation A, we infer a conclusion which is absurd. In other words, we have seen negation connective in the premise, but in the conclusion negation is not coming. The other is, suppose we have double negation A, not A, then we can infer A. I go on to explain all the other truth connectives. Let me introduce once again conjunction. Given the truth of A and another sentence B which is also true, we can infer the conjunction of A and B or B and A. That's possible. We can also eliminate conjunction in our inference. That is, given a conjunctive sentence A and B, we can infer one of the conjuncts A or another conjunct which is B. Now let me also explain the function of disjunction. Given a sentence A which is proved to be true, we can infer a disjunctive sentence A or B. Or given a sentence which is true, let us say B, we can infer another complex sentence which is actually disjunctive sentence A or B. There is another case in which we can eliminate disjunction or disjunctive connective. Suppose we have A, and on the assumption that A is true, we are able to derive C. And let us suppose that there is another sentence B which is true, and then we can derive C from that supposition again. Then, given the proof of A or B, we can infer C. In other words, in our inference, we have already eliminated disjunction. Now let us come to conditional or so-called implication. I'm going to introduce implication. Let us suppose that there is a sentence A and it is true, and basing on this supposition we derive a sentence B. Then we can infer the conclusion A implies B. The other is one of elimination of conditional connective. Let us say that there is a thesis, that means a sentence which is true. A implies B. In another thesis, A, that is A is true. Then given these two sentences, we can infer the truth of B. Along this line, we can introduce what is so-called biconditional connective, or sometimes called as material equivalence. Now look at this thing. A materially equivalent to B, which is definitionally equivalent to A implies B and B implies A. In this way, with the given truth connective, that is implication, we have just explained biconditional connective. Let me explain what are those symbols, especially those alphabets A, B, C, which occur in the derivations or inference. Those letters A, B, C, which we have employed to explain connectives, are called meta variables. A, B, C are not part of our object language or the so-called formal language which we have constructed. Rather, these meta variables stand for sentences in the object language. Another thing is, what are these meta variables? You can ask. Meta variables are the vocabularies of meta language. And what is meta language? In fact, now I am delivering my lecture in English. English is the meta language for object language called logic. So ABC, being part of the English alphabet, is meta variable for our language, which is language of logic. There is another symbol which needs explanation. You may have noticed square brackets whenever we are using some kind of meta variables, A or B, C, whatever. Now some are used without these square brackets, but some are involving square brackets. What are the functions of these square brackets, or what are these square brackets? Actually, these are supposition. Square brackets are supposition. So when I have A within brackets, I'm not saying that A is actually true or it is a thesis in the language, but that we are assuming the truth of A. So let us look at the disjunction, where we introduce where we eliminated a disjunction. So we are assuming that if A is true, and then we can derive C, and also another sentence B, we are assuming the truth of B, and then we can derive C from this. Then given A disjunction B, we can infer C. Now what is happening here is this, that these brackets are a marker to tell us that whatever is coming within the bracket is just a supposition, they are not true. But in the inference, we are eliminating our assumptions. So in none of the conclusion that we have arrived, we will not see square brackets. There is another peculiar symbol which looks like inverted A. This is called lambda in Greek alphabets, and this also needs explanation. So take a look at this symbol. Now let us look at the function of this lambda. And by using this peculiar symbol lambda, we have explained negation connective. How are we to understand this lambda? I have said before that lambda is a very peculiar expression which stands for some kind of absurdity. That is a statement which is absurd, and this absurd statement is different from contradiction. So this absurd statement, as I said, is different from a contradiction. A contradiction will look like this: P and not P. This is sheer contradiction. But an absurd sentence will look like this: 1 is equal to 2. this is not a contradiction. Or when we say a part is bigger than the whole, it is an absurd statement, but it is not a contradiction. But with the help of this lambda, we are introducing negation connective. What we are trying to say is this, that if we assume the truth of, let us say, a sentence A, and then on the basis of this truth we have arrived at certain contradiction, that means our initial assumption is false. I think you're getting me. We begin with the assumption that A is true, and then if we arrive at certain absurd statements, that means our initial assumption that A is true is false. So that is how a negation is introduced in the inference. There is another function of this lambda which has not been explained in any of the modules before or so far, even in this module. Given an absurd sentence, we can derive anything. So here the symbol lambda, then we infer D. D is any sentence, true or false. In other words, from an absurd sentence, we can infer anything whatsoever, true or false sentences. Now, the peculiarity and the interesting thing about this lambda is this. Is this a logical connective? If so, how are we to understand this? Actually, it's not connective. This is interestingly connected to certain philosophical problems. How are we to understand negation? And that problem is there in Indian philosophical logic and even in Western philosophical logic. But in the symbolic study of any logical system, this has not been explained. Though this has interesting metaphysical implication, for want of space and time, we will not venture into those philosophical speculations, and we will limit our explanation of lambda here. Now we have introduced all the truth functional connectives. You may have noticed that some of these connectives have occurred in the modules we have done before. For example, introduction of conjunction and elimination of conjunction. They are known by different names. Introduction is called conjunction and elimination is called simplification. But that is not called natural deduction system. Only in this module we are calling it as a natural deduction system because of this reason. In the modules that we have seen before, for every connective we have not introduced the rules for introducing and the rules for eliminating. But in this we have seen that for every truth connective we have introduced rules for either introduction of connective or rules for elimination of connective. This module has been named as natural deduction system, and we have seen in the earlier modules that there are already rules for conjunction. For instance, introduction of conjunction is explained as rule of conjunction, and also rule for elimination. Elimination rule for conjunction is also known by the name simplification. In the modules that we have seen before, we have already encountered these rules, like rules of conjunction. Here we have a different name. We say introduction rule, and then we introduce conjunction, or elimination rule, and then we do away with conjunction. But in the modules that we have seen before, those are known as rule of conjunction and simplification respectively. But what is the difference between the modules that we have seen before and this one? It is this, that in this system we have introduced the rule of introduction and rule for elimination for every truth functional connectives, whereas in the modules that we have done before, we have not done that. So this is why it is called natural deduction system. In other words, the founder of this system, Professor Genzen, he thinks that this kind of reasoning is so natural to our reasoning process, and this in some sense exhaustively works out all the inference rules possible in any deductive system. So that's why it is called natural deduction system. Now, given this set of rules, we can now see what we can do with these rules. Let us have a look. We can give a proof that A is materially equivalent to double negation A or not A. Suppose we have three assumptions. So that means they will be coming under brackets. A, one assumption, second assumption is not A, and the third assumption not A. Now, given this assumption A and not A, we can, by application of negation elimination, derive absurdity, some kind of contradiction. Now, by looking at the assumption number 2, which is negation A, and we can now look here from assumption number 2, which is negation A, and given absurd sentence, that is lambda, we can, by the right application, with the right application of negation introduction, we can derive not A. Given not A, and looking at the assumption number 1, which is A, with the introduction of implication, now we can infer A implies not A. Let us go towards the right side. Assumption number 3, not A, with the help of elimination rule of negation, we can infer A. Now, with the help of introduction of implication, we can infer that not A implies A, and we can now discharge our assumption 3. So given these two derivations, A implies not A and not A implies A, with the introduction of conjunction, we can infer the conjunction of these two expressions. A implies not A and not A implies A. And by definition, which I have explained before, that if A implies B and B implies A, it is definitionally equivalent to A implies B. In this case, because they imply each other, A is therefore materially equivalent to not A. Let us now try another proof. A implies B implies C, together implies A implies B and A implies C. How do we give a proof of this sentence? For this, we need a set of assumptions again. Assumption 1, A implies B conjunction A, first assumption. Then another assumption A. Given this, with the help of elimination of conditional connective, we can arrive B conjunction C. That is, if A implies B and C and A is given, we can infer the consequent, that is B and C. Now, given B and C, by appealing to the rule of elimination of conjunction, we can derive B from B and C, and also C from B and C. Now let us go on further. Just look at the sentence above. Now we can introduce implication again. So look at the assumption number 2, A. So if by assuming A we can arrive at B, then by rule of introduction of conditional, we can infer A implies B. Likewise, Given our assumption A, if we are able to derive C, by the application of the same rule, we can infer A implies C. Now, if we have these two sentences, A implies B and A implies C, then we can introduce conjunction and join these two sentences, which is what we have seen here. A implies B and A implies C. Given these two sentences, now we can look at our first assumption, which is A implies B conjunction C. So, by introduction of implication, now we can infer the implication, which is A implies B and C, whole thing implies A implies B and A implies C, which we have derived from the earlier step. So this is how by these rules of introduction and elimination we can prove the truth of any sentence within the system. Now you have seen what we can do with this natural deduction system. What is novel here is this, that we are no longer appealing to extra linguistic factors for checking the validity of any arguments or the truth value of a sentence. Given the rules, we are just looking at the possible ways we can make our inference, and we have explained all the inference rules, and with the help of those inference rules we are now able to check the validity of any argument within the standard truth functional sentential logic, or also we can check the status, that is truth value of any sentence given these rules. So this method is purely syntactic, and so it is called syntactic approach to doing standard truth functional sentential logic. Now we are almost ending this module. Before that, I want to give a summary of what we have learned. In the modules that we have done before, we have taken a semantic approach for checking the validity of any arguments. But in this module, we have presented a set of rules by application of which we can check the validity of any arguments without having to appeal to anything outside that language, that is without truth function or truth conditions, but by just appealing to the rules, that is how an inference can be made involving connectives or without connectives. We have introduced a way of doing logic without semantics. In other words, we have abandoned the use of semantics in this system. This is a purely syntactic approach to doing logic, and because this is also so commonsensical, it is called natural deduction system. Thank you.